So hey everyone, I'm JD Maloney. I'm the lead storage engineer here at NCSA. We uh, do a lot of work with HPC storage systems. NCSA is known as the National Center for Supercomputing Applications. We're located on the University of Illinois' Urbana-Champaign campus, which is the flagship campus for the University of Illinois system. And NCSA was founded in 1986, closing in on 40 years ago. So we've been doing HPC work for a long time. The University of Illinois itself, where we're kind of co-situated with, is a very, very busy research institution. It's an R1 class research institution, the highest level research institution defined by the NSF and other granting agencies. So we have a lot of active research that goes on our campus. And yeah, that's kind of where we're situated. We operate systems like Delta. We operated systems like Blue Waters and a lot of others. We provide HPC compute, high throughput computing, and then research storage, as well as expert support for research scientists across the United States via things like the Access program, formerly known as Exceed, and through many other numerous engagements with federal granting agencies, as well as some industry partners. We run systems for multiple Fortune 100 companies here within our data center. We're also highly involved in research software development. There's a software director within NCSA that does a lot of work with research software and promoting good software and research computing. So that's kind of the high level background. So in terms of what our archive needs are to service these types of fields and users that we work with, researchers constantly are generating a lot of data. That's happening at more and more staggering rates. It's a lot easier. We're in a very agricultural, busy state, and so there's a lot of data we gather from things like drones that fly over farm fields where they're taking imagery and viewing crops from above as they grow and storing that. We also do a lot of work with NASA and some other astronomy-based projects where there's a lot of high-resolution satellites and telescopes that are generating a lot of data and more data than we've ever seen before from those types of instruments. Those things were usually historically smaller data sets. They took a lot of images, but due to transmission limitations between either outer space and the ground, or just via other means getting data from other countries where satellites are sometimes built like South America, the images were usually smaller. But as high-speed networks have kind of come of fruition, we're seeing a lot more data out of those instruments as well. A lot of campuses, I know we're not unique in this, there's a lot of MRI machines and cryo-EM machines, which can generate terabytes of data in a single day. We have petabytes that are generated every quarter from these types of machines. And then, of course, there's all sorts of other types of sensors and cameras that are out there that researchers are using and finding novel ways to do the research and to gather data to help solve problems. Not all this data, though, needs to be active or warrants capacity on primary tier space, especially as that data ages after collection. Obviously, when data is collected, it's usually of high interest there in the beginning, but as time goes on, it usually gets delegated out of the primary tier and into an archive tier that we'll be talking about here in a moment. This archive tier, though, is important because keeping data around for even after it's of immediate active use has multiple reasons. Obviously, researchers are obviously improving their software all the time and reprocessing their data at a later date with better algorithms can be very helpful, especially in the rise of AI right now. We're seeing a lot of old data sets get resurrected and processed again with algorithms that are more GPU centric, where they're looking through images trying to find patterns that they didn't search for before because they just didn't have the algorithms to look for those things back in those days. And so keeping data around for just those reasons has proved interesting for researchers. There's also compliance with grant requirements. A lot of, at least in the United States, a lot of federal granting agencies are pushing for researchers to keep data around for a longer period of time and keep that data available, not necessarily on active storage, but available such that they can be downloaded by other people. They want to make sure the data is around to be reproducible so that other scientists can try and reproduce results that a different scientist had done earlier, and making sure that the data is around so that that's possible is important to these granting agencies. And so being in compliance with them requires us to have that kind of capacity. So those are kind of some of the big reasons why we want to keep data around and is important. But open academic research, as many of you probably know or would surmise, is very cost sensitive. It's not a profit centric situation. So it's very much I kind of shoelaces and duct tape kind of a thing where we kind of have to keep data around for a long time, but with not a lot of funding. And so archiving to tape can meet that need, especially at scale, because it's obviously a very cost-effective way to keep large amounts of data around. And restore requests for these data sets can be frequent on popular data sets. So having a way to handle popular data set downloads is also something that we've wanted to make sure that we scoped for when we were designing this system, because sometimes researchers want to get a large data set out fairly quickly sometimes. So our system, as Megan mentioned, is named Granite. It is a large tape archive system. It's a 19-frame spectrologic T-Finity system that sits on our floor. Currently, there are 30 TS1140 tape drives in there, and those are very old. We are about to upgrade to 20 by LTO9 tape drives here soon. So those should be due to arrive in the data center here sometime in late April or early May. So we're doing a large media conversion here within the library here very soon, and we're very excited about that. There's a DDN disk cache that sits in front of this unit. It has metadata on SSD, and then the capacity of the disk cache resides on hard drives at this time. And currently have about a petabyte of disk cache space that's there. And our ScoutAM nodes are currently Dell R740s. We have 5 of them that are the movers. They each are going to be attaching to 4 LTO9 tape drives directly. There'll be no fiber channel switch between. There'll be a direct connect between the tape drives and the mover nodes. So that's what our current system looks like from a hardware perspective. So this is a resource that is there for Illinois researchers to store data long term that may be useful years later. We're also opening the system up soon to be allocated via Access, starting in summer of 2024. For those not in the United States, Access is like a federated research infrastructure platform where researchers can apply for allocations and get space, in this case, capacity. It also allocates compute resources for researchers that need compute. So this will be opening up Granite to not just Illinois researchers, but also to researchers across the United States to store data long-term here, starting pretty soon. So its goal is to preserve these unique data sets on a durable media to ensure safety of these data sets for later use. So we do run dual copy on these. We'll talk about that in a second, but its main goal is to preserve this data and keep it safe for a long period of time. We did build it to be performant enough to act as an online repository for large data sets. So the system is optimized for recall at the expense of ingest in some cases. And so as we kind of discuss this a little bit here in the next couple of slides, the main reason we made some of our decisions was because we want to make sure that we're being very conscious of what the path to recall looked like. We want to make sure that users can get data back quickly, as quickly as we can possibly get them that data back. So some of the key configuration details in terms of how we have configured this system. We do have a fairly high drive count of 20 LTO9 drives. This gives us about 9 gigabytes a second of throughput at peak if all drives are humming along at their maximum space. We do have slots available in this TFIN to add more drives if we need to. We're not anticipating we'll need to, but we do have the chambers available for more tape drives if we need them in the future. We do write 2 copies of data for durability, but this also increases the recall speed based on how we place these TeraPacks within the TFIN unit. It can shorten the distance that the robotic library has to move to grab those tapes to do loads. Each allocation that we allocate on the system is given a separate tape pool. If it's a big enough allocation, it gets its own tape pool, or if it's a very small allocation, like say 1 terabyte or a 2 terabyte allocation, it might share a tape pool with a couple other smaller allocations. The goal of this being is to greatly reduce the number of tapes that a given data set sits on. So when it goes to recall, it reduces the number of tape mounts that we have to do to get that data back. A lot of the latency and a lot of time can be had in having to juggle tapes around, having the library move tapes back and forth. And so keeping the data from getting spread out across a large number of tapes, even if it's a small data set, we want to prevent that from happening. So that's why we are containing allocations into a small as possible tape pool using ScoutAM. That's a very key part of our configuration. So also how we do caching. Our system currently has a fairly large cache. 1 petabyte is a fairly large system for a disk cache in front of a tape library, but this will likely shrink. Our hope is to move to an all NVMe based cache tier, but make it smaller. Obviously not put a petabyte of flash, that'd be a lot, but have a smaller but very fast flash tier that sits in front of this system. And we're currently treating this disk cache as if it were small, even though it is large. We're kind of glossing over that fact in terms of how we operate the system with policy, and we're aggressively flushing data to tape, and we're also aggressively releasing it from the cache. So that cache does not fill up very much. It's a fairly empty, large cache, and that's just kind of keep the library operating as it will operate when we do eventually shrink that disk cache and speed it up. So data that is inbound to the archive, we've found is seldom reread in the near term. So we're working on monitoring the frequency of requested assets, and we want to pin some of our popular data sets into that cache when possible, especially the smaller ones to facilitate fast retrieval. A lot of times what will happen is a research group will store data in Granite as a data set, and they'll announce a data release to their science community, whatever their area of science is. And then there'll be kind of a period of time over the next weeks to months after that announcement of the data release where other scientists from other institutions across the country or the world want to go and download that data set to see what's in it based on that science release. And so we do want to coordinate with those projects, and we try to coordinate with those projects when they're going to do those data releases so that we can try and pin those data sets up into a little bit of a faster tier such that we don't have to stage data in and out a lot or churn through that data and stage it multiple times to facilitate moves if and when we can help it. It's not always possible, but we do try and coordinate that when we can. So that's kind of how we manage the cache in terms of our use case there. So some of the features that we are leveraging within ScoutAM, we're leveraging a lot of them. I kind of hit a couple of our favorites here. I didn't want to belabor it too much, but we're doing a lot of work with Ben and all the others at Versity on the new S3 Gateway. We're really excited about that feature that Megan just talked about. So the ability to treat the file system as if it were kind of an AWS Deep Glacier system, but without having to pay for the fees costs that AWS charges for retrieval is very appealing to research teams, as I kind of just alluded to in my prior slides. So having that S3 interface in the front end, I guess we're maybe using it conventionally, Megan, I guess, hopefully, or maybe the way that you'd envisioned, is very exciting for our researchers to have that in front. So also there's some research teams that treat Granite as their second copy from a primary copy that lives somewhere else on campus. And a lot of backup tools these days are written with S3 protocol as an outbound connector built in. So there's a lot of popular backup tools out there that will do tiering to S3 for archive. And so having an S3 endpoint in front of Granite allows those applications that some of our other teams run to point archive at the Granite system and put data on there as well. So, and this also provides users with a lot of options for tools that they can use on their end to transfer data. There's a lot of different tools out there that speak S3, just like there's a lot of backup tools that I mentioned earlier. There's also a lot of just kind of end user tools that make it very nice to interact with data in an S3 manner. And so it's appealing for researchers in that regard as well. So we're very excited about leveraging the S3 gateway features that are being developed right now. And then lastly, Archsets. I think this is might be my last slide of content. Archsets are very important to us. That kind of allows us to do that tape pool control that I mentioned earlier. Allows us to control which media various collections land on to reduce that data spread across tapes. And this is actually getting increasingly important to us as our tape size gets larger. We're going from 4 terabyte tapes up to 18 terabyte tapes. So this is even more critical thing for us. So we use Archsets extensively. And these provide us with a lot of flexibility as to how and when data gets staged out to tape and when it leaves the cache. And then also it gives a lot of flexibility as to just where the data lands, like I mentioned. And yeah, it's just a very flexible and extensible way for us to perform data management kind of at a large scale. It isolates data well, and it helps us integrate with our automation. Part of our automating for our allocations on the system is we'll look at free tapes that are formatted for ScoutFS, and we will create pools out of them, usually 2 pools per allocation, and then we'll set up the Archset to send data for a given path into those 2 pools and replicate data that way. So we make very heavy use of the Archsets in ScoutAM for our researchers. Oh, yeah, so I do talk about future plans here. So some things that we do have kind of coming up for ourselves with regard to Granite on the roadmap that Megan showed earlier were quotas. We're very excited about directory quotas or quotas in general, especially with larger tapes. We need a method for capping usage of these allocations right now. With 4 terabyte tapes on TS1140, it's been easy to kind of just say essentially using the tape pools as the containment device for our different allocations to make sure they don't go over their quota or over what we've allocated them on the system. But as tapes get bigger, it's going to be a coarser grained control. And so having quotas within the ScoutFS file system would be very helpful. So we're very excited about that. We can't always rely on group ownership of data. Sometimes if you look at like group quotas, which is why we're really excited about directory or what are called like project quotas. Sometimes, so that's why we're very excited about those specifically. And this will provide us also better metrics about the utilization of the system. And we'll also be doing quotas most likely on both capacity, but also on inodes. One of our interfaces for the system besides S3 is a tool called Globus, which you may or may not be familiar with. It's an easy web interface to transfer data back and forth between large storage systems. Those tools can make it really easy for users to try and ingest hundreds of thousands or even millions of small files into the Granite archive system, just because they can select a top-level directory that has a lot of data beneath it and hit the big blue arrow button that starts the transfer, and then they walk away, and they don't realize what they've just done sometimes. And so setting inode quotas as well will be something that we'll hopefully be doing as well, so we can kind of help prevent users from shooting themselves in the foot either on data egress or just in general on treating the archive with some respect. So, and our goal mainly is to also help make sure that users are prepackaging their data in a way that makes sense. So enforcing these quotas helps users maybe think a little bit about how they need to be bundling their data via tar or something else as they ship data into. Not that they need to onto the archive, but we're trying to help users make sure that they're being intentional about their data management on the system. So we're very excited about rolling those out. And then also ingest automation from primary storage. We have some other primary storage file systems that are very fast, that are mounted on our HPC systems. And we're trying to help users come up with more and better ways to move data automatically between the primary tier and Granite. We like that they're separate namespaces. We don't like combining namespaces between our archive and our primary file systems. Keeping them separate helps just from data integrity and reliability. And if there's a failure of one namespace, we want to make sure that you have the data safe in the other namespace. But we want to help users more easily move data back and forth between these tiers. So we want to provide them with tools. And so we've been looking at a lot of the Versity API and other tools that Versity is kind of exposed to help us better help users move data quickly into and out of the Granite archive system based on their needs. And also the way the data gets packaged on the tapes has helped make this go faster as well, so that the Archsets kind of come into play here and help us increase this ingest speed for researchers, both on the way in and on the way out as well. So we're really excited about continuing our efforts there and making use of Versity's tools for getting data in and out. So, and then also for allocations processing, like I mentioned before, given our rigid Archset policies, setting up allocations can be tedious. And so like we're essentially having to manually choose which tapes we want to go into each of these pools. And so using the Versity API for creating all this is something that we've been working on with our allocations team. They're very familiar with provisioning capacity on large POSIX file systems like Lustre or Storage Scale or Ceph or other things. But we're working with them to extend those tools into the Versity API for provisioning capacity automatically within the Granite system. So that'll speed up the time that it takes for researchers to request, from time between when a researcher requests their data allocation space and when they can actually start using it. And getting that time window shortened is obviously beneficial for helping support them. So